Welcome back to CAD Level 2 Assemblies and Design for Manufacturing. In the previous two modules, we set the stage by getting you ready for this workshop and giving you an appreciation for why we need to use tolerancing when using multi-part assemblies. In this module, we'll start our hands-on activity, a pair of joints fastened together using an M4 bolt and nut. You already know the drill. Let's break this down into its features. And so, let's start with making the joints. Let's hit the ground running by breaking down our joints into its constituent features, a process that we're already familiar with by now. I'm going to start by creating a cube base for our joint. In order to do that, I need to start a sketch, and I can start that sketch on the top plane. It's an arbitrary choice. I'll choose the top plane. I want to align my view normal to the sketch plane so that I'm looking straight down on it. And now I can choose how to draw my rectangle. I'm going to start with a center point rectangle, simply because modeling about the origin is a valuable lesson that we learned last time. I'm going to place my center, drop the corner, and now I'm ready to define it as a cube. Now I'd like to show you a shortcut. Normally, we would choose the dimensioning tool to create a dimension bubble that defines the width or the height of this square. But you'll notice that when I first place my part, I'm given the option to directly edit the length of an edge right after having dropped it. If I don't press anything else after having dropped the corner of this rectangle, and I press 3, enter, a dimension will be inferred on that edge. It now gives me the opportunity to edit the second side, but we know better than this. What we want to do is use the equals constraint to select one edge and the remaining edge as equal in length. Now we have our square. Now we have our 3-inch square. Let's extrude it. I'm going to accept my changes, move into an isometric view, and select the extrude tool. Now, I want to show you something new. Let's say, for example, in between having created my square and wanting to extrude that square into a cube, I went and I took a break, say to eat a sandwich or something. When I come back, I can't quite recall that I had made my cube 3 inches on its sides. Rather than guessing at the sides, or having to go back and measure it each time, let's create a dependency between the depth and the width and height that we created for our square. I'm going to have to go back out of my extrude tool for now, and come up here to this new tool called Variable. When I click on Variable, it asks me to name my variable. I'm going to call it Cube, and then I can define the value of this variable as 3 inches. You'll notice that since I'm in length mode for my variable, the value needs to be a length. It can be in any length units, but it does need to be a length. I'm going to accept this change. And now, the way that this variable works is that I can use the value cube rather than a number in any value that I use in any subsequent features. Right now, cube comes after sketch 1 in the features list, so I need to move cube up above sketch 1. Now, when I go back into sketch 1 and edit this length, rather than 3 inches, I'm going to say #cube. Now the width and height of my square is defined by the variable cube rather than a specific number. When I come back out of the sketch mode and into extrude, when I select my square, I can set the depth to be #cube. When I do that, it automatically assigns the value of cube, 3 inches, to my square's height. Pressing accept, I can exit the extrude, and I can see that I have a 3 inch by 3 inch by 3 inch cube, or at least it looks that way. But how do we confirm that that's the case? Down here in the bottom right hand corner is a measurement tool. If I click on any feature, a face, or an edge, or a point, I can get measurement information on that feature. You'll notice that by clicking on this edge, the measurement reports 3 inches. Similarly, if I click on this face, the area of that face is 9 inches squared. which suggests to me that this length and this length are both 3 inches. And no surprises there, that is the case. What if I wanted to change my cube size? All I need to do now is go back into Cube, change it to 1 inch, and my changes will propagate through my part. Now, we know better than to leave features unnamed. So let's rename these quickly. And now, let's move on to those lobes. I'd like to lean further into our review of what we did last time. And so rather than extruding some circular profiles, let's use a revolve. That means that we'll have to draw some rectangles on top of our cube and revolve those rectangular profiles along an axis between these 2 midpoints. So, let's do that. Starting with a sketch, I'm going to select the top face of my extrusion. Naturally, I'm going to choose to view normal to sketch plane. And now let's create our rectangles. I'm going to choose a corner rectangle this time, and infer that one of the corners of my rectangles is going to be coincident with the corner of the square. Placing an arbitrary rectangle here, I'm now going to show you another new tool. To give you some insight into what I'm trying to accomplish, I'm going to revolve this rectangle and a rectangle mirrored across the center line of this square up and over to create a lobe. I'm then going to revolve a third rectangle in between these 2 rectangles, such that I cut a cylindrical channel in between these 2 lobes. So, in order to do that, let's copy and paste this rectangle 3 times in a line to the right. Up here on the toolbar, we see the option Linear Pattern. When we select it, we can use our paintbrush tool to select all of the edges of our rectangle. And now it asks us the details of our pattern. Right now, there are 3 rectangles being patterned 1 inch apart to the left, and no rectangles being patterned down. You see that the Linear Pattern tool asks for 2 dimensions at right angles to one another. If I click and drag this arrow, I can adjust the spacing between these rectangles. Similarly, for argument's sake, I can click and drag this arrow to create a pattern in an orthogonal direction. Since we aren't actually interested in this except for showing off this feature, I'm going to return this value to 1 times, suggesting that there is only 1 row in our grid. Now, with 3 rectangles aligned to the right, I'm going to leave this measurement arbitrary, and you'll see why in a moment. This isn't the only way that we could do this, but I want to show you something. I'm going to accept my pattern by left-clicking. You see that little green checkbox on the icon of the mouse? Now that I've accepted that pattern, you'll see that my rectangles are ready to be defined. For now, I'm going to erase this dimension, because I want to ask some questions about how we could use constraints here rather than physical dimensions. What needs to be true about these rectangles? Well, they need to be equal in size, and that's already part of the patterning tool. So, step 1 accomplished. As I had said before, we need these rectangles to be butted up against each other. So, let's take this left edge of the center rectangle and the right edge of the leftmost rectangle and make those edges coincident. Next, I know 2 things. First, the right edge of my rightmost rectangle needs to be aligned with the right edge of my cube. Second, if I'm to revolve these 2 outermost rectangles, such that they create cylindrical lobes aligned with the geometry of my cube base, I know that this center line needs to be the revolve axis by which I revolve them. That line needs to be centered on my cube. So, to show you a new tool, let's kill 2 birds with 1 stone. Up here is the Midpoint Constraint. When I select it, I can select this point and this edge to lock that top right corner of my rectangular pattern to the midpoint of this farmost line of my square. Quick sanity check. All of our lines on our sketch are black, suggesting that our sketch is fully defined, which is what we are aiming for every sketch that we create. Since we're done, let's exit out of our sketch give ourselves a nice isometric view, and start revolving. Using the Revolve tool, I'll extrude the lobes first. I need to choose my revolve axis to be this center line, and there we have it. Now, you'll recall that I need to revolve cut this center rectangle out such that I create a negative indentation for this lobe. However, you'll notice that my sketch disappeared now that I've consumed it. In order to use sketches again, I can hover over a past sketch and select Show Sketch 1. When I do that, my sketch reappears and I can continue using it. Selecting Revolve and choosing Remove, I can choose this center rectangle, choose its revolve axis, and now I have a divot ready to accept my mating joint. Future uses of the sketches that I've made visible will now leave my sketches visible, so in order to tidy up my workspace, I'm going to re-hide this sketch. Now, we can repeat this problem exactly, inverting the add and remove options for the outside and inside lobes to create the mating lobe. However, let's save ourselves some time. If I right-click on Part Studio 1, this tab that contains the part document for my first joint, I can duplicate it and all of its features. Now, when I move over to this copy, I can simply edit my revolves such that Revolve 1 is a remove option and Revolve 2 is an add option. Let's do some tidying up in our workspace by renaming everything. First, starting with the names of our tabs. And that gives us our two joints. The last feature we should add is a hole for an axle to be threaded through, such that the joints can be joined together. Let's create a sketch on the right-hand side of this lobe. We would like to place our axle directly in the center of this larger circle. I want to show you a new tool, which is called the Use Project Convert tool. Using the Use Project Convert tool, I can click on geometry that exists on different sketch planes, projecting them onto the sketch that I'm working with. If I click on this inner circle of the inner lobe, I project the perimeter of this circle out to my sketch plane. While I'm here, let's look at something else called the Construction tool. Construction lines allow you to create geometry as a reference, rather than something that will physically be effective in an extrusion or a three-dimensional tool. When I click on this bottom line and choose Construction, you'll notice that the line turns into a dotted line. This line now only exists as a reference, rather than something that we can do something with. This tends to help declutter our workspace and prevent us from having to select multiple faces when using the Extrude tool. However, right now, we're not going to use the Extrude tool. I want to add one more feature, a point, at the center of this circle. With our point added, let's exit the sketch and move over to the Hole tool. In the previous workshop, we used the Extrude tool to cut our holes. Now, let's use a more sophisticated tool. You'll notice that rather than selecting a sketch region, we are simply asked to select a point on our sketch. If we select this point, a hole is generated. You'll see that this hole is drilled all the way through our part. This is because the termination option in our hole is set to through. Blind or blind and last will give us an option to select a depth. For now, let's leave this as a through hole. The size of our hole is defined by these options. When using the custom option, we can simply designate the diameter of our hole using a numerical value. However, if we choose a different option, say ANSI, ISO, DIN, or PEM, these acronyms are standards for sizing fasteners. ANSI is the standard for fasteners measured in the imperial system, like inches. ISO is the standard for metric fasteners. Let's use the ISO standard, since we wanted to use an M4 bolt for our axle. Here, we can choose the hole type and the size. Let's choose M4 first. Now, we can choose the hole type. A tapped hole is the proper size for adding threads to our hole. A clearance hole gives our M4 bolt plenty of room to wiggle around. And a drilled hole will ask us which size drill we want to drill with. Since our axle should be static with respect to our outer joint, and should allow the inner joint to rotate freely, let's use the tapped option for the outer joint and the clearance option for the inner joint. Here, in the tapped option, we can choose the pitch of the M4 screw that we're using. Let's just use it with the default. When we accept our change, our axle hole is drilled all the way through our joint. Now, let's do the same thing for joint B. As we did before, let's place a sketch. I'm going to choose this outermost edge, just to drive the point home of using this Use tool. When I project the circular profile of this inner lobe and turn it into a construction line, you'll notice that the region inside of the circle changes from a light gray to, well, clear. If I toggle back and forth between construction and non-construction lines, you can see that the region inside of the circle, when it's under construction, is not considered an extrudable region. Finishing our sketch, let's move on to the hole. Now when we choose our hole, let's define our hole type as clearance. This will allow the inner lobe to rotate freely along the axle. You'll notice that the thread pitch no longer matters. This is because the thread is no longer threaded across the bolt. We're simply loosely sleeved over it. Accepting this change, we're ready to mate our parts. But before we get too far, I want to show you something fun and something that will help us better visualize our assembly. You'll notice that down in the bottom of our features list is a parts list. Each part in our studio is named and listed down here. Right now, our Joint A part studio only has one part, Part 1. Similarly, our Joint B part studio only has one part, Part 1. When we combine these parts together, you might notice that it's not only going to be difficult to differentiate the two based on their part name, but also based on their color. Let's fix that. First, let's rename this part. Next, let's colorize it. I'm going to right-click on the part name, or on the part itself, and choose Edit Appearance. Let's select a color, press Accept, and now our joint is not only named properly, but is colorized in order to differentiate the two parts in our assembly. I'll do something similar for joint A. And there we have it. In our next module, we'll join these two parts using what are called mates.